Okay, any questions about what we had done on Monday? You see, what we were discussing was we were looking at the atom. Okay, I mean, if you think of historically, we first discovered the alpha particles. So we had a new kind of probe to look at the atom itself. And then we, of course, tried to understand what the atom was, and it kind of gave us a surprise. It told us that there was a very dense core of the atom. So the atom has a very dense core, and it also has electrons, and electrons should be, we also know more or less the size of the atom. So the size, and the nucleus is known to be at least 4 orders of magnitude smaller than the size of the atom, so the electrons should be around. Well, this was at least one consequence of the observation. There were other observations like the emission and the absorption spectrum. Basically, absorption spectrum is if you send white light through a gas made up of a particular kind of atom, after the white light passes through, we would see some gaps in the spectrum. The white light contains all the frequencies. Whereas when we let it pass through a gas, well, some of those frequencies are missing. Or another thing we can do is we can just, for example, send electric light through electric current through a gas, through the same gas. And in this case, the gas will emit light. And when you look at the spectrum of the emitted light, it only emitted at discrete values. And those emitted values in fact coincided with the absorbed values in the previous absorption spectrum. And it was also found out that the wavelength had a very simple pattern. The inverse wavelength was proportional to some constant and the differences of 2 integers. So it had a very simple relationship. So the question was, how can we understand all of these phenomena? So at the same, more or less at the same time, we had these new ideas about the wave nature of particles. And we were trying to apply this wave nature to understand the other phenomena that we were observing in nature. Well, this will be one of them. And that phenomena, that new understanding was telling us that the electron behaves like a wave. So how can we apply this wave principle to understand the atom? So that is the main question. So we already looked at the particle in a box. If you remember when we were discussing the particle in a box, we said that, okay, it's natural to expect that if there's a wave inside, it should be 0 at the boundaries, just like the waves on a string. So if this is possible, only if an integer multiple of half wavelength fits into this width. So in this case, if this is 0L, the total length is L. L should be an integer multiple of half a wavelength. And we derived all the discrete energy levels. Now let's try to apply the same principle to the electron orbiting the nuclei. Now, of course, the principle will be slightly different. You see, we don't have just a linear string, but a circular string. And in this case, let's just take one string. Let's assume we just fit half of a wavelength. And furthermore, let's just assume that we put that string in a circle. What will it look like? So if this is the circle we have, you see, the string in this wave goes to one side of this circle, one side of the string, and then comes back. It never crosses to the other side. So if we would start from here, we would go to one side, and then we would just close it. This cannot be. This is not this is continuous, but not differentiable. I mean, in physics, everything kind of should change smoothly. Well, let's go to the other case. Well, this was another wave that we could fit on a string of length L. So you see, the wave goes to one side. At the middle, it goes to the other side and then closes. So now the wave kind of can close smoothly on itself.
Yeah, what exactly is the circular?
The orbit. The orbit. We are assuming that we are making a very simple model. Classically, the electron, let's say, is just going around a circular orbit. Well, now it's a wave. Actually, the wave should be going around. So in the circle, there should be a wave. Of course, the wave is not just at a single point and moving around, but at every point, just like standing waves, they are continuous. Their shape doesn't change with time. We expect more or less the same thing over here. The wave should close on itself. So that is basically what this argument is about. So you see here, in the first case, the wave doesn't really close on itself. If you continue with the wave, this is what you get. In the second case, the wave does close on itself. And then it just repeats the same pattern. So it just doesn't change. So the condition of standing waves on a circular loop is, difference from that the total length should be an integer multiple of half a wavelength. The circumference should be a multiple of a full wavelength. This is called Bohr's quantization condition. Well, for the time being, this is just an assumption, a postulate, so to speak. It's not really a proof. It's just, what I have said is just saying that this argument is plausible. But is it correct? To test whether it is correct, we have to compare it with experiment and see what are the consequences of this postulate. So let's see. 2 pi r, the wavelength is the de Broglie wavelength of the electron, which is h over the momentum. Or we can also write this in this form. P times r is equal to n times h over 2 pi. N times h bar. This combination is what we call h bar. So what is PR? Do you remember? No, not the numerical value. I mean, we had defined the momentum times the radius as some other quantity. Or we can also write it, if it is non-relativistic, m times v times r. It's the angular momentum. So essentially what Bohr says is that the angular momentum should be an integer multiple of h bar. So just like the energy was quantized in units of h nu, what Bohr's postulate is that the angular momentum of particles should be quantized by multiples of h bar. Okay, so now this is just one of the consequences of our initial postulate. Now let's try to find what are the possible energies of the electron. Now we will be mixing classical concepts with new quantum physical concepts. You see, if we are imagining this circular orbit of the electron, classically speaking, the central acceleration, the central force, is provided by the electrostatic force. If there's let's say the atomic number of the nuclei is Z, there are Z protons, so the force will be ZE squared over R squared. So this is one condition we have for V and R. V and R should satisfy this condition. Well, if this is satisfied, let's cancel these. So mv squared, this is equal to 1 over 4 pi epsilon 0 ZE squared over R. But this basically also tells me in terms of the energies, the kinetic energy of the particle, of the electron, which is 1/2 mv squared. This is minus 1/2 the potential energy of my system. You see the potential energy, this is nothing but minus the potential energy. The potential energy is negative because we have two particles of opposite charge. So the total energy of the system will be the kinetic energy plus the potential energy, which is minus half the potential energy plus the potential energy, or half the potential energy. 1 over 4 pi epsilon 0 ZE squared over 2R. So if we can find the radius, then we can also determine the total energy of my system. Now let's go back. So this is one condition we have between the speed of the electron and the radius of the orbit of the electron. And the other condition we have is 2 pi r should be equal to an integer multiple of h over mv. This is the other condition we have. So to find the energy, I would be interested in finding the radius. So let's try to eliminate the velocity in favor of the radius. So v should be equal to an integer multiple of h over 2 pi m, or let me write it as h in terms of h bars. H bar over m times the radius. Let's just put it over there in our force equilibrium. So the mass times n squared h bar squared divided by m squared r squared, this should be equal to 1 over 4 pi epsilon 0 ZE squared over R. So this tells me that the radius of the circular orbits of the electron cannot just take any value. They can only take the value 4 pi epsilon 0 h bar squared over ZE squared m times n squared. Let me put a small n over there to denote that it essentially corresponds to the value, that radius corresponds to a given value of n. So the radius of the orbits cannot take any value, they should take these particular values. Now this number is usually called the Bohr radius. 4 pi epsilon 0 over E squared times h bar squared over m. And so for hydrogen, our n is just A0 times n squared. Now also keep in mind that, you see, all these constants in A0, they're just fundamental constants of nature. So the radius of the orbit is inversely proportional to the mass. So a couple of years ago, for example, there was all this excitement about the discovery of the Higgs particle. So what would happen if the Higgs particle didn't exist? Well, if the Higgs particle didn't exist, essentially the electron would be massless. But if the electron is massless, and if m is equal to 0, well, we won't have the atoms. There won't be any circular orbits allowed for the atoms. Now let's go and see what are the possible energy values. You see, the energy was given, the total energy. Yes.
Momentum hocam relativistik almamızın nedeni klasik fiziğin yeterli olması mı? Approximation yeterli olması.
Yes. Well, at least now we know the speeds, we know the radius. Corresponding to this radius, you can calculate the velocities over here. And the speed of the electron just turns out to be less than 1% the speed of light. So at least we know that assuming the electron to be non-relativistic is consistent. So the electrons in the hydrogen atom, at least, they are not really moving at relativistic speeds. Yes. Well, you see. Well, if you want to insert the Z is over here. It's for the hydrogen atom, Z is just 1. So, well, this is the allowed radius of the orbits of the electron in the hydrogen atom. Well, if you want to put the allowed radius for an arbitrary atom, just divide it by Z. Well, let's start with the simple ones, and then we will see. Well, the energies, these were 1 over 4 pi epsilon 0. Z, let me insert the Z again, Z e squared over 2r. Now let's say Rn. This is equal to 1 over 4 pi epsilon 0. Z e squared over 2. Well, 1 over Rn is just e squared Z e squared m over 4 pi epsilon 0 h bar squared times n squared. Now 1 over n squared. Or let's say En is equal to E1. Sorry, I made a mistake somewhere. There's a minus sign over here. E1 over n squared, where I had defined E1 to be the coefficient. Let's say 1 over 4 pi epsilon 0 squared. There's a 2. There's a Z e squared squared m over h bar squared. And in fact, E1, if you just calculate it, this is minus Z squared times 13.7 electron volts. For the hydrogen atom, Z is just 1. So the electron in the hydrogen atom just cannot have any energy. It can only have these energies, just like the particle in a box example. Because when we were discussing the particle in a box, the particle could only have different energy values, discrete energy values. In that example, the energy change proportional to n squared, an integer squared. In the case of the hydrogen atom, or in fact any atom, the allowed energy values changes as the inverse n squared, 1 over n squared. Now, what about the spectrum? You say, first of all, does this answer some of the questions that we imposed? Like, how come the atom be stable? You see, if the nuclei is at the center, the electron is orbiting around it, classical physics tells us that since the electron is accelerating, it should emit electromagnetic radiation, and hence it should lose energy. So its orbit should spiral to the atom, inside the atom. And we just don't have any atom left. But you see, here what we see is the radius of the atom just cannot be arbitrary. It can only take discrete values. So it cannot just spiral down and fall onto the nucleus. It's just not allowed. How about the spectrum? Why do we see the discrete spectrum? Well, how does the atom emit electromagnetic radiation or absorb electromagnetic radiation? Basically, you see, here you have the energy levels. The energy levels and whatever you have. So let's say this is the zero energy. Which basically corresponds to R goes to infinity. The electron is, you can say that the electron is now free. It's at infinity. And the minimum possible energy for the hydrogen atom is minus 13.7 electron volts. And then the next level will be just 1/4 that value. Oh, sorry, not there. It's somewhere over here. The next level will be here. The next level here. And here they will be almost continuous. So this is E1. This is E2. This is E3. This is E infinity. So these are the energy levels. So the electron can only have these energy values. Now, so how can this electron emit some photon, lose some energy? Well, the only way, we know the energy conservation, if the electron starts from one energy value and it makes a transition to some other energy value. So the electron initially, it can have this much energy. Finally, it loses some of the energy in the form of a photon, and then the electron has the remaining energy. Now, the allowed frequencies are given by this difference. So the atom cannot emit a photon of arbitrary frequency. It can only emit photons having that frequency. Or in terms of the wavelength, you see nu is just c over lambda. So hc over lambda should be equal to E1, 1 over n final squared minus 1 over n initial squared. Or 1 over lambda should be equal to minus E1 over hc times 1 over n initial squared minus 1 over n final squared. No, here I made a mistake. This is n initial minus n final. And what was experimentally observed was the observed wavelengths, whatever the series you have, were essentially r times 1 over some integer squared minus some other integer squared. Now we know what those integers are and what this constant is. And if you just put in the numbers, you see E1 depends on epsilon 0, h bar, and the mass of the electron. Everything that we already know from measurements, from different measurements. So we can just put in the numbers over here and compare it with the experimentally measured value of R. And the discrepancy was in the fourth digit, I think. The third or the fourth digit after the point. There was still a discrepancy, though. That is something we should discuss. But at least the first 3-4 digits, they perfectly matched. So at least this is a confirmation, let's say, that our initial postulate, an observation in favor of our initial postulate, that it was most probably correct. So the various series we have, you see, remember, we had the Balmer series. 1 over lambda was R1 over 2 squared minus 1 over n squared. This basically, this series arises because of the electrons that fall into the second level. So if you just imagine all these energy levels of the hydrogen atom, an electron from the third excited state, the second excited state, from the third level, can emit a photon and go back to the first excited state. Or an electron having this energy can go down to this state, or an electron from this state can go down to this state. You see, here they are almost continuous. This is essentially what we observe as the Balmer series. Well, of course, they don't have to go to the first excited state or the second state. They can also go to what's called the ground state. This is the first excited. This is the second excited state. So an electron starting from the first excited state can go down to the ground state. From the second excited state, it can go down to the ground state. From the third state, it can go down to the ground state, etc. So you have all these series. And these are what we call the Lyman series. So you see, the Lyman series have 1 over lambda, the same R, 1 over 1 squared minus 1 over n squared. Balmer, 1 over lambda, 1 over 2 squared minus 1 over n squared. This is the in the visible spectrum range. The other ones are not visible. So now we explain it. We started with, already we had the assumption of the wave nature of the particles. Using that wave nature and plus this postulate that an integer multiple of a wavelength fits into an orbit, we could see at least some of the problems posed by the observed spectrum, both the emission and the absorption spectrum. Any questions? Well, okay, this is my wire. Okay. And I need some help. Hold it there. So just imagine there is this full wave. Okay? Here it is down, here it is up. And here it is just crossing the zero. Now I fold it. Okay. Hold this. Oh. Making the circle now here. So you remember, at this region I was below. At this region I was above. So it just now becomes some kind of a circular shape, like this one. So You see, what I do is, this is, in this sense, this is below. So you just fold it like this. If I fold it like this part remains inside the ring, this is outside the ring. And so if I started from, there is one, these 2 points are the same points, they are so-called nodes. My wave is 0 at those points. In the middle, my wave is also 0. So at this point, my wave is 0. At this point, my wave is 0. And since if I close it like this region stayed inside. It is just this part. And this region stayed outside my ring. It is this part. Yes?
I don't understand that. How can we say that it's still differentiable after making this a circle?
Why not? Well, you see, this is just a sketch. I mean, this shape is not exactly that shape. It's to obtain that one from this one, I had to stretch some. You see, this length is smaller than this length, one thing. But at least the idea is, just take this as an analogy. The idea is that if we can somehow identify a wavelength, meaning a repetition of the wave itself, the wave should repeat itself after one round. Okay, that is what we define the wavelength, right? Or the wave should start repeating itself after half a round around this ring. Or the wave should repeat itself after 3 rounds after going around this ring. So that is why we have the total circumference. Now, if the electron goes around this ring once, it should start repeating itself. That's the idea. Yes.
To say that we have some specific radius values, we use the electromagnetic force idea. Also, Maxwell's equations say that charged particles accelerate, charged particles lose energy. So I understand why it can't be, but I don't understand why.
Well, basically, we are not just modifying the Newton's dynamics. We are also modifying the Maxwell's equations, in a sense. As you said, classical Maxwell theory tells us that every accelerated particle should emit radiation. Here now we are changing that. So we are saying that a charged object can emit a radiation only if it makes a transition from one energy state to the other energy state. Of course, there is a question. How come classical Maxwell equations turn out to be so successful? They work, except that in these particular cases. How can there be, in a sense, a transition from these discrete energy levels to the continuous energy levels, where we have the Maxwell's equation, which states that, classical Maxwell theory, which states that every accelerating charge should lose energy. Now let's discuss that. Now there are other questions in this picture, other questions that this picture does not explain. But let's start with this so-called the correspondence principle. Yes? Well, you say experiment does, these are the experimental results. Okay, these are experimental results. So we don't know. The experimental results just tell us that, okay, there are these numbers corresponding to various wavelengths, and those wavelengths seems to satisfy such a pattern. The experiment doesn't tell us why do we have these integers? Why do we have the squares? What is this radius? Well, not radius. What is this constant, Rydberg's constant? That's not what the experimental tells us. Experimental only tells us that, okay, this is what we observe. Now, on the theoretical side, we try to understand what those integers correspond to. And now at least Bohr's model tells us that these two integers essentially correspond to the initial excitation quantum number and the final excitation quantum number. So that is our theoretical interpretation of this.
They have the same pattern, energy level, and in light, the same energy, the same pattern.
You mean in the Lehman and the Balmer series?
Yes.
And the theoretical prediction? Yes.
The spectrum and the energy, split energy levels have the same pattern.
Yes.
In nature.
What do you mean in nature? This is what we observe in experiment, if you call this one in nature, yes. And can we explain those phenomena theoretically? This is what we obtain theoretically. Now, what the next step would be to interpret our theoretical results. So, and if you just compare these two, basically why we observe this pattern? Well, our theoretical understanding is that we observe this pattern because this pattern arises from electrons from excited states going down to the excited states. Each excited state specified by some integer number. But we don't go and see the electron, oh, it's in the excited state, now it goes to the ground state. We don't see that. This is what we see. And this is what we expect to see. If this picture of the electron being de-excited from some quantized energy levels is correct, this is what we expect to see. And this is what we actually see.
Hala, Ivan over HC'nin o discrepancy'si nereden geliyor?
We will come to that. Well, let's start with that one, with the discrepancy in R. You see what we assumed here? We assume a fixed nucleus and there's an electron orbiting around it. What will the atom, will the nucleus be fixed? What fixes the nucleus? Nothing. The nucleus can move, and it does. So you see, if you have this two-body problem, so we have this one mass, another mass, they will be orbiting around each other. Well, in fact, not. They are not really orbiting around each other. What they are orbiting around is they are actually orbiting around their center of mass. So the nucleus will make a circle around the center of mass. The electron will make a circle around the center of mass. So this is what will actually happen.
But the proton and the electron, I mean, the nucleus is much, much heavier. I mean,
Correct.
The center of mass is almost in the proton. Does that slight change can do that?
Well, let's see how much will be the change. You see, this problem will be actually equivalent to a problem. Here we have a large mass. Here we have a small mass. This is, you can actually show that it is equivalent to this problem. You have a fixed force center, and the electron is orbiting around that fixed center. But the electron has a mass mu, which is given by the product of the masses divided by the sum of the masses. This is what's called the reduced mass. Okay, this is something that you should have discussed in 109. Well, as your friend points out, do you remember this? No, you should have seen that. You see, let's see. Let us just make a short detour. On one hand, you have this force, mR1. Double dot is equal to F1. And then you have the, let's say, M1, M2, R2, which is minus F1, and we will be assuming that these forces depend only on the difference. So it's just the Newton's second law and the third law. If two masses are exerting forces on each other, it should be equal magnitude, just opposite in direction. Now, rather than working with R1 and R2, let me define two different coordinates. Let me call small r, R1 minus R2, and capital R to be M1 R1 plus M1 R2 divided by M1 plus M2, the position of the center of mass. Well, let's see. No, this is M2 R2, sorry. Now, what is the acceleration of the center of mass? Well, this will be M1, the acceleration of R1 plus M2 times the acceleration of R2 divided by M1 plus M2. But this is nothing but 0. Because this is F1, this is minus F1. No, this is F1, this is minus F1. Their sum is just 0. Center of mass doesn't accelerate. Well, this is something that we already know. If there are no external forces, the center of mass, the acceleration of the center of mass will be 0. The more interesting thing will be, what is the acceleration corresponding to that small r, the separation between the two? Small r acceleration is R1 double dot minus R2 double dot. This is equal to 1 over M1 times F1 plus 1 over M2 times F1. Well, here I have a minus sign. Another minus sign is over there. So this is equal to 1 over M1 plus 1 over M2 times F1. So F1, by the way, depends only on the radial separation. So this R double dot is equal to 1 over mu F1. And this 1 over mu is 1 over M1 plus 1 over M2. Or mu is equal to M1 M2 divided by M1 plus M2. Now, what did we achieve? You see here, if you look at our original equations, to solve for R1, we need to know R2. To solve for R2, we need to know R1. So these are what are called coupled equations. They depend on each other. You cannot just solve one of them. You have to solve both of them simultaneously. But now we have two other equations. R double dot, the capital R double dot. We already know the solution. It doesn't depend on anything else. And the equation for small r, it only depends on small r. It doesn't depend on anything else. This equation is independent of our other equation. So now we have before we had two coupled equations, now we have two uncoupled equations. And in fact, this is nothing but the Newton's second law for a particle of mass mu, with the center of force fixed. So before, when we were looking at the energy levels of the hydrogen atom, we were assuming the center of force was fixed, which actually it's not. But the only thing we need to do is we have to repeat all the derivation with using the reduced mass. Just not the mass of the electron. If we use the reduced mass, well, here the center of force is fixed. Everything should be the same. The only difference will be here E1. Instead of m, we should use mu. Let's say E1, 0, divided by E1 mu is actually m over mu. Or let me write the other way around. With the reduced mass inserted, without the with the mass of the electron inserted, it's just mu over m, or the mass of the nucleus divided mass of the nucleus plus the mass of the electron. Now, of course, as your friend has pointed out, this is a very small number. You see, the mass of the proton is something like 2,000 times more than the mass of the electron. And this number is actually 0.99, I think, 5. It's very close to 1. But the question is, this will shift the wavelengths of the emitted radiation. So, is your equipment precise enough to determine that wavelength? You see, nowadays we can determine the wavelength very precisely, and so precisely that we define the meter in terms of a multiple of wavelengths. And another thing is, let's say, let's just compare hydrogen and deuterium. The difference between the hydrogen and deuterium is that this mass is twice in deuterium, because the deuterium is made up of a proton and a neutron, not just a single proton. So this ratio, the correction factor for deuterium will be different. So actually that was how deuterium was discovered. Since that number will be different from this one by less than 1 per mil, if you can measure the wavelength so precisely, you can determine the mass of the nucleus of the atom that created that radiation. Any questions? Questions?
How did we define atoms or nucleus wave which only using mass?
Well, you see, let's go back.
Sadece dalgayı anlayabiliyoruz. Dalgadan, daha doğrusu enerji nedeniyle anlayabiliyoruz. Bizim ölçeklerimiz şey olmak değil mi?
Yes, that's what we are measuring. We are not measuring the wave. No. We are just trying to obtain a description of nature whose predictions are consistent with our observations of nature. We don't see the wave. We see, for example, the emission spectrum. We see the scattered alpha particles.
We know only mass. We can understand radius from mass. The radius of electron.
Well, eventually, I will say that we even don't understand that. You see, this is a model. This is, let's say, the first step after our plum cake model of the atom. This model still, well, let me just make one correction, another correction. This solid curve over here, this is not the trajectory of the electron. In this model, it's the dashed curve that is the trajectory of the electron. The solid curve is the wave accompanying the electron. It's the de Broglie wave. And just like quite often we draw photons as wiggly lines, it's not that the photon is moving along a wiggly line. The photon is going straight. It's the wave that is oscillating up and down. Now, eventually, probably in a couple of weeks, I will say that the electron doesn't even have a trajectory. You see, writing such a trajectory, even if it is such a dashed line, I'm saying that I know the position of at least one of the coordinates of the electron, the radius. But then we have all kinds of uncertainty relations. If I know the radius, I don't know the radial momentum. If I don't know the radial momentum, I cannot say that the electron is continuing around this circle. So this is, in a sense, just one step, one baby step in our quantum mechanics. And as I said, eventually I will say that the electron doesn't even go around the circular orbit. It doesn't even have a trajectory.
Hocam, borunun nasıl bulunduğu ile ilgili bir sıkıntı
Okay.
Hidrojenin bir sonraki enerji seviyesinde hidrojen bir orbitte bulunmaması lazım. Yani artık elektronun fırlaması lazım.
Why?
Çünkü başka enerji seviyesi var mı?
Sure.
Kendi orbitinden koptuktan sonra artık free elektron olmuyor.
Well, let's see. All of these are different energy levels.
Ama başka bir orbitin yapabileceği başka bir yer yok ki orada bilsin. Direkt sonsuzdan mı biliniyor?
No. In fact, you see, it can have this much energy corresponding to the A0 radius, Bohr radius, or it can have this radius, which is 4 times the Bohr radius, or it can have this radius, which has 9 times the Bohr radius, or it can have this radius, which is 16 times the Bohr radius. So the electron can have many different energies in the hydrogen atom. It doesn't have to be ionized. In fact, if you want to ionize the hydrogen atom or separate the electron from which is at the ground state, the energy you have to provide is at least 13.7 electron volts. That's called the ionization energy. You see, if the ground state electron, it has this much energy, E1 over n squared, which is a negative number. No, E1. In the ground state, n is just 1. Ionization energy for ground state hydrogen this is essentially how much energy you should give if you want to ionize this hydrogen. This is equal to minus E1. Now, you see, now, when we were looking at these series, for example, the Balmer series, if this is a given wavelength, then we said that it can have this value, 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 etc. And there is a limit to this. It cannot have, and that limit, you see, 1 over lambda is 1r times 1 over 2 squared minus 1 over n squared. You see, in that limit, n is infinite. Well, if n is infinite, then this, is that the smallest or the largest wavelength, by the way? Largest. Are you sure? Hmm? Hmm? Is it increasing or decreasing? Hmm? You see, if this is the expression, does the separation between different wavelengths, it decrease or decrease as you increase n? Well, you see, as you change n by 1, this number change is very small if n is very large. So here, the change in the wavelength is very small. That is, the change in this one should be very small between two different wavelengths. But that happens only if n is very large. So n is large, that means the initial state has a very high energy. In fact, it's almost a free electron. If almost a free electron emits a photon and goes to the ground state. That is how you get that limit. But not all these lines correspond to a free electron emitting a photon and going down and being captured by the hydrogen atom. It's an excited electron, not necessarily free. You see, we had this plot over here. You see, we have an electron having this much energy, who is at a radius 9a0 squared. It goes down to another orbit with a lower energy, with a radius 4a0 squared. Then you get an emission. So none of these electrons are free. They don't have to be free.
Yanlış hatırlamıyorsam Bohr bir elektronun dışındakileri açıklayamıyordu. 2 elektron açıklayamıyordu. Onun sebebi o circle çizen wavelength'in interference'e çok karışması mı? Yani 2 tane elektron olduğu zaman 2 tane wave olacak. 2 tane wave olursa da birbirine interference'e bir circle oluşturulacak.
Well, you see, there are a couple of problems with this picture. Well, this is a very simple picture. One of them is, well, if you have another electron, that's a three-body problem. We don't know the trajectory. Second problem is, here we just considered circular orbits. But if you look at, I don't know, the planets, the orbits need not be circular. Why should there be only circular orbits? Why don't we allow other kinds of orbits? These are some of the shortcomings. Another shortcoming of this model is that, well, even if here we said that we have these discrete levels, well, that's not all of the story. If you just look at, let's say, take one of them and enlarge it, well, there you see a couple of lines. Not just a single line, but there are a couple of them. Why? Another thing that we don't know is these lines have different intensities. Well, the Bohr just tells us, the Bohr model tells us only that at which frequencies or at which wavelengths we should have these lines, but it doesn't tell us anything about their intensity. How can we compare their intensities? So in that, I mean, the Bohr model, okay, it's great. It explains some of the observations. At least that gives us confidence that we are in the right track. But it cannot be the whole story, because there are many other questions that this model doesn't explain. Well, in this course, at least we will see why do we have this splitting. And why do they have different intensities? Well, that probably you will see in quantum physics or mechanics.
Hocam enerjideki belirsizlikten mi geliyor? Delta H çarpı delta T'den mi geliyor?
You see, uncertainty is kind of a continuous change. These are discrete.
Ama enerji seviyelerini kesin belirledik. Nasıl? Yani belirsizlik ilkesine göre kesin belirleyemememiz lazım.
Well, you see, these states essentially live infinitely long. There is an uncertainty. You see, even these lines, they have some thickness. They're not just single wavelength. They have a very small thickness, which is determined by how long does the electron stay in this excited state. If the electron just gets de-excited immediately, then, as you had said, the uncertainty in the energy will be large. If it takes a long time to get de-excited, then the uncertainty in the energy will be small. Well, the uncertainty in the energy, due to the energy-time uncertainty, is smaller than the separation here. So it's not a big deal.
Hocam peki belirsizlikten dolayı bu iki enerji seviyesinin arasında da yani elektron durabilir diyebilir miyiz? Yani öyle bir sanal bir enerji seviyesi var mı?
No. And yes.
Hem de.
Well, we will discuss a bit of quantum mechanics. So there, ask your question again. You see, how does the electron make a transition? So here we only talked about the possible energy states that the electron can have. But we didn't discuss how can the electron make a transition? How can we describe it? No. Here, you see, this is the larger wavelength. No, smaller wavelength, sorry.
Verilen enerji arttığı için verilen enerji.
You see, as n increases, as n increases, this number gets larger because I'm subtracting a smaller number. If this number gets larger, meaning 1 over lambda gets larger, so lambda gets smaller. Okay, let's give a 10-minute break, and then we will continue.